December 23rd, 1944. The frozen plain southeast of Bastogne. Captain James Parker of the 420th Armoured Field Artillery Battalion watched through his binoculars as a German column emerged from the tree line 2 miles distant. Panzer IV tanks, perhaps a dozen of them, flanked by half-tracks carrying infantry and towed anti-tank guns. A textbook combined arms formation, advancing with the confidence of veterans who'd survived 3 years on the Eastern Front. Parker's battery of M7 Priest self-propelled howitzers sat hull down behind a slight ridge, their 105mm tubes elevated and ready. His forward observers had called in the coordinates. The German column was moving through open farmland. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Probably assuming the Americans lacked the artillery ammunition to contest every approach to the besieged town. They were about to discover how catastrophically wrong that assumption was. Parker gave the order his gunners had been waiting for since the restrictions lifted 4 days earlier: load posit. The breech blocks of 6 howitzers slammed shut on shells, equipped with the most closely guarded technological secret in the American arsenal: variable time fuses, proximity fuses. The Germans had no idea what was about to hit them. The first salvo screamed skyward at precisely 10:47 hours. The shells arced through the grey winter sky, climbing to their apex before descending toward the advancing column. But these rounds weren't aimed at the tanks themselves. The fuses contained miniature radar systems that would detect the ground beneath them and detonate the shells exactly 30 feet above the frozen earth, transforming each projectile into an airborne fragmentation bomb covering thousands of square feet with lethal steel. What happened next would be recounted in German after-action reports with words like incomprehensible and terror from above. The shells detonated in perfect sequence above the column. The panzer crews, buttoned up inside their steel boxes, survived. The infantry marching beside them did not. Men who'd learned to hit the dirt at the first whistle of incoming artillery found that all their combat instincts were useless. The fragments came from above, shredding anyone in the open. Within 90 seconds, Parker's battery fired 48 rounds. German casualties approached 300. The panzers, stripped of their supporting infantry, reconnaissance elements, and anti-tank gun crews, ground to a halt. Without infantry protection, they became vulnerable to American bazooka teams. Without reconnaissance, they couldn't identify threats. Without their towed anti-tank guns, they couldn't establish defensive positions. The column retreated in disorder, leaving their dead scattered across a half-mile of Belgian farmland. The Germans had just encountered a revolution in warfare they hadn't anticipated and couldn't counter. The problem confronting German armour commanders in the winter of 1944 was brutally simple. They'd built their tactical doctrine around combined arms integration. Panzer divisions weren't just tank formations. They were complex organizations balancing armour, mechanized infantry, artillery, engineers, and reconnaissance in carefully calibrated proportions. Remove any single element and the entire system degraded catastrophically. This organizational philosophy had evolved from hard lessons learned in Poland, France, and especially Russia. German planners understood that tanks alone couldn't hold ground, couldn't clear obstacles, couldn't defend against infantry anti-tank weapons. The Panzer Grenadiers, the mechanized infantry who accompanied the tanks, performed these critical functions. They cleared buildings, established security perimeters, protected the vulnerable rear aspects of tanks from infantry with shaped charge weapons. The standard German tactical manual specified that Panzer IV and V tanks should advance with infantry no more than 50 to 100 meters distant. The infantry moved in half-tracks or marched beside the tanks, ready to deploy immediately when resistance was encountered. Anti-tank gun crews in towed weapons followed close behind, prepared to establish defensive positions if the advance stalled. This formation had proven effective across thousands of miles of Eastern Front combat. American artillery doctrine, as it existed through most of 1944, struggled to effectively engage such formations. Traditional high-explosive shells with contact or mechanical time fuses required direct hits or near misses to cause casualties. Infantry accompanying tanks learned to disperse. They maintained intervals. They used terrain. A typical American artillery barrage firing contact-fused shells might kill 3 to 5% of infantry in the open with a battalion-level fire mission. The mathematics were unfavorable. To suppress or destroy a German combined arms formation required enormous expenditures of ammunition, time, and forward observer coordination. Weather complicated everything. The winter of 1944 brought some of the worst conditions in decades. Cloud cover prevented aerial observation. Snow obscured terrain features. Forward observers couldn't accurately adjust fire. They couldn't see landing. German commanders understood these limitations and exploited them ruthlessly. They moved under poor visibility. They attacked during snowstorms. They knew American artillery, while numerous and mechanically reliable, operated under predictable constraints. Contact fuses required precise targeting. Time fuses required visible burst observation for adjustment. Neither worked well in December weather over the Ardennes. This tactical reality shaped the German operational plan for Watch on the Rhine, their December offensive. Intelligence assessments calculated that American artillery, while present in large quantities, couldn't achieve the fire density necessary to stop massed armored formations in poor weather. The plan called for rapid penetrations, exploiting gaps, with lead elements bypassing American strongpoints rather than reducing them through direct assault. Speed and momentum would overcome firepower. The mathematics seemed sound. American infantry divisions typically fielded 54 105mm howitzers and 12 155mm howitzers. Impressive numbers, but distributed across a divisional frontage of several miles. Concentrate a Panzer division's full strength, roughly 160 tanks and 70 self-propelled guns, at a single point, and the Americans couldn't generate sufficient fire density to stop the breakthrough. What German planners couldn't know, was that American artillery was about to receive a weapon that would invalidate every calculation in their operational plans. The variable time fuse had existed for over 2 years, primarily employed in anti-aircraft roles where its revolutionary capabilities were obvious. A radio fuse that detected proximity to aircraft and detonated automatically multiplied the effectiveness of anti-aircraft artillery by factors of 5 to 10. But the Pentagon had strictly forbidden ground artillery use over continental Europe. The reasoning was straightforward. If a dud round fell into German hands, their scientists might reverse engineer the technology. German possession of proximity fuses could make Allied bomber operations over Europe prohibitively expensive, perhaps impossible. The strategic bombing campaign depended on numerical superiority. Level that playing field with technology that multiplied Luftwaffe anti-aircraft effectiveness, and the entire air war calculus collapsed. Security protocols reflected these fears. Every VT-fused shell carried unique serial numbers. Production facilities operated under Manhattan Project-level secrecy. Workers couldn't discuss their tasks even with family members. Military police guarded shipments. The fuses were treated as strategic weapons equivalent to radar or cryptographic systems. Their battlefield employment was restricted to circumstances where recovery by the enemy was unlikely, primarily anti-aircraft use over water. By late 1944, American factories were producing 40,000 proximity fuses daily. Enormous stockpiles accumulated in European supply depots, officially designated POSIT in Army logistics documents. Artillery units knew the fuses existed. Forward observers understood their theoretical capabilities. But standing orders prohibited their use in ground combat roles over land. The technical specifications of the Mark 53 VT fuse, designed for 105mm artillery, represented a remarkable engineering achievement. The complete unit measured just over 4 inches in length and weighed 14 ounces. Inside that compact package, American engineers had assembled 130 electronic components, including 4 miniature vacuum tubes no larger than a small finger. The radar system operated on a principle of transmitted and reflected radio waves. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. An oscillator tube generated a continuous radio signal through a small antenna at the fuse's nose. This transmission bounced off any nearby surface, the ground, buildings, vehicles, or personnel, and returned to the fuse where an autodyne detector received it. When the returned signal strength indicated the shell was within the optimal fragmentation range, typically 25 to 35 feet above the target, a trigger circuit activated the booster charge. The engineering challenges had been extraordinary. The acceleration forces when a shell leaves a 105mm howitzer exceed 20,000 times normal gravity. Electronic components designed for radios sitting in living rooms had to be completely redesigned to survive this violence. Vacuum tubes, those fragile, glass constructions, required special mounting systems using rubber cushions and reinforced filament structures. Power came from a battery activated by the firing shock itself. Inside each fuse, a small glass ampule containing electrolyte sat in a cavity. The crushing acceleration when the gun fired shattered this ampule, allowing the electrolyte to flood a reserve battery that would provide power for the shell's flight time, typically 20 to 35 seconds for standard trajectories. The entire system had to function while spinning. The rifling in a 105mm howitzer imparted approximately 3,000 rotations per minute to the shell. The fuse had to maintain stable radio transmission and reception while rotating at this speed, in temperatures ranging from -20 to +30 degrees Celsius, with electronics exposed to severe vibration and shock throughout the flight. Quality control procedures rivaled pharmaceutical manufacturing standards. Each fuse underwent multiple testing stages. Resistance checks verified circuit integrity. Spin testing in centrifuges simulated flight conditions. Dummy drops onto concrete tested shock resistance. Reject rates in early production exceeded 30%. By late 1944, sophisticated manufacturing processes from RCA, General Electric, Sylvania, and dozens of other contractors had reduced rejects to under 5% while production volumes reached industrial scale. The cost per unit in 1944 dollars was approximately $18 for the fuse alone, not including the 105mm shell body, propellant charges, or shipping containers. An entire proximity-fused round cost roughly $32 compared to $8 for a standard contact-fused high-explosive shell. But battlefield effectiveness wasn't measured in dollars, it was measured in casualties inflicted per round fired. Standard doctrine for 105mm howitzers employed several types of ammunition depending on the target. High-explosive shells with contact fuses for hard targets like buildings or bunkers, smoke rounds for screening and signaling, white phosphorus for incendiary effects, time-fused airbursts for anti-personnel work, though these required forward observers to adjust the fuse settings based on actual burst observations, a technique that worked poorly in bad weather or when observation was limited. The arrival of VT-phased ammunition eliminated the observation requirement for effective airbursts. The shell automatically detonated at optimal height regardless of weather, terrain, or visibility. Battery commanders didn't need to estimate range and set mechanical time fuses. Forward observers didn't need to observe and adjust burst heights. The fuse did the mathematics automatically using radar feedback. This automation had profound tactical implications. Artillery batteries could deliver effective airbursts on the first salvo. Time of flight from gun to target for a 105mm shell at maximum range was approximately 30 seconds. With proximity fuses, that meant effective anti-personnel fire could arrive on target within 45 to 60 seconds of the fire mission being called, allowing for plotting and gun laying time. No adjustment salvos. No waiting for burst observation. Immediate, devastating effect. The fragmentation pattern from a 105mm shell, detonating 30 feet above the ground, covered approximately 150 feet in diameter with lethal fragments. Each shell contained roughly 4 pounds of Composition B high explosive, surrounded by the shell casing, which fragmented into thousands of pieces traveling at velocities exceeding 3,000 feet per second. Fragments retained lethal energy out to 200 feet from the burst center. A 6-gun battery firing in unison placed 6 such burst zones on target within seconds. Standard procedure called for fire-for-effect missions to consist of at least 4 salvos, 24 shells. This created overlapping fragmentation coverage that no infantry formation in the open could survive. German soldiers who'd learned to survive Russian artillery barrages on the Eastern Front found that all their experience was useless against proximity-focused fire. But in early December 1944, these shells sat in ammunition dumps from Normandy to the Rhine, forbidden from use. Forward artillery commanders watched German offensives develop and knew they possessed a weapon that could stop them cold. The bureaucratic resistance to authorizing VT fuse employment in ground combat persisted even as German armor broke through American lines on December 16. The American artillery situation at the start of the Battle of the Bulge was precarious, but not desperate. The German offensive achieved complete tactical surprise, but American artillery units maintained organizational cohesion even as infantry positions collapsed. Field artillery battalions, the organic artillery assigned to each infantry division, generally managed to displace rearward in good order, maintaining communication with higher headquarters and protecting their equipment. The terrain of the Ardennes, densely forested with few good roads, created natural choke points. German armor had to follow limited routes. American artillery could interdict these routes even when frontline infantry positions had been overrun. But the traditional approach, firing contact-fused high-explosive shells at road junctions and likely assembly areas, required enormous ammunition expenditure for limited effect. The Germans were experts at dispersion and camouflage. What changed the tactical picture was Colonel Oskar Alfred Axelson's decision on December 16 near Monschau. His 406th Artillery Group supported the 38th Cavalry Squadron, a light reconnaissance unit that was being overwhelmed by elements of the German 326th Volksgrenadier Division. The cavalry troopers were outnumbered and outgunned. Conventional artillery support wasn't stopping the German assault. Axelson made a command decision that technically violated standing orders. He authorized the use of proximity-fused shells from his artillery group's stocks. The results were immediate and dramatic. German infantry advancing in traditional assault formations encountered airburst artillery fire for the first time. Casualties were catastrophic. The attack stalled. The cavalry position held. Word of Axelson's action reached higher headquarters rapidly. The tactical effectiveness was undeniable, but Axelson had violated explicit orders against using the classified ammunition over land where duds might be recovered. The staff debate was intense. Some officers wanted Axelson court-martialed for unauthorized use of classified material. Others recognized that the weapon worked exactly as advertised, and the tactical situation was desperate enough to warrant accepting the security risk. General Dwight Eisenhower resolved the debate personally. On December 19th, after receiving detailed reports of the effectiveness at Monschau and assessing the overall Bulge situation, he formally requested authorization to employ proximity fuses across the entire theater. The Pentagon, recognizing that German armor had achieved breakthrough and American ground forces needed every possible advantage, approved the request on December 21st. The authorization came with conditions. Artillery units were instructed to use VT-fused ammunition only in situations where extensive ground recovery by the enemy was unlikely. In practice, this meant using them freely in active combat zones where American forces maintained pressure but avoiding their use in areas that might be abandoned to German control. These restrictions loosened rapidly as the tactical benefits became apparent. Distribution began immediately. The American logistics system, perhaps the most capable military supply organization in history, delivered proximity-fused ammunition to artillery units across the Ardennes within 48 hours. The stockpiles already existed in forward depots. Transportation assets, primarily 2.5-ton trucks, moved ammunition from depots to battery positions. By December 23rd, most American artillery battalions in the Bulge theater had received their allocation of posit ammunition. The 420th Armored Field Artillery Battalion, equipped with M7 Priest self-propelled 105mm howitzers, received 600 proximity-fused rounds on December 22nd. Battery commanders conducted quick briefings, explaining the fuse's capabilities and tactical employment. The key point was simple. These shells automatically airburst, no fuse setting required. Fire for effect immediately. Results would follow. Captain Parker's engagement on December 23rd became a template for proximity fuse employment against German armoured formations. The tactic wasn't to target the tanks directly. High explosive shells, even airbursting ones, couldn't penetrate tank armour. But combined arms formations required their supporting infantry, reconnaissance elements, supply columns, and gun crews. Proximity-fused artillery systematically stripped German armoured units of everything except the tanks themselves. Infantry marching beside the panzers died in the open. Half-track crews were killed when fragments penetrated the thin armour of their vehicles. Towed anti-tank guns lost their crews to airburst fire. Supply trucks carrying ammunition and fuel burned when fragments punctured fuel tanks or detonated exposed ammunition. The psychological effect was devastating. German veterans knew how to cope with artillery. Dig in, use cover, wait for the barrage to lift. But proximity-fused fire made cover worthless, unless it was overhead cover, and the Ardennes in winter offered limited overhead protection. Foxholes that protected against contact-fused shells became death traps under airburst fire. Tree lines offered concealment but no protection. Fragments came from above. German after-action reports from late December 1944 contain repeated references to new American artillery techniques. Unit commanders described fire that seemed to possess intelligence, that followed retreating troops, that struck precisely where men sought shelter. These weren't exaggerations, they were accurate descriptions of proximity-fused artillery's effects. The Wehrmacht's tactical response doctrine, developed over years of combat, emphasized rapid movement and dispersion when under artillery fire. Infantry learned to scatter, to use terrain, to avoid clustering. These techniques reduced casualties from conventional artillery by significant margins, but against proximity fuses, dispersion only spread casualties across a wider area. The fragments found targets regardless of spacing. Consider the engagement on December 24th near Bastogne, involving the 969th Field Artillery Battalion. This was an African-American unit commanded by Lieutenant Colonel Hubert Barnes, equipped with 105mm howitzers. German forces from the 26th Volksgrenadier Division were attempting to tighten the encirclement around Bastogne. Barnes's battalion received orders to interdict a German assembly area identified by forward observers. The battalion fired 240 proximity-fused rounds in a 15-minute fire mission. German casualties exceeded 400 killed and wounded according to prisoner interrogation reports collected days later. The German unit, a reinforced regiment that should have numbered approximately 2,000 effectives, lost roughly 20% of its strength in a quarter hour. The attack never materialized. The unit required 48 hours to reorganize before it could return to offensive operations. The effectiveness metrics were extraordinary. Standard calculations for artillery effectiveness suggested that killing a single enemy soldier required approximately 2,000 rounds of conventional ammunition under field conditions. Variables included target dispersion, use of cover, weather, and visibility. Artillery was fundamentally an area weapon, effective for suppression and disruption but requiring massive expenditure for actual destruction. Proximity fuses changed these calculations dramatically. Field reports from artillery battalions in the Ardennes showed kill ratios improving by factors of 5 to 10, where conventional fire missions might inflict 5 to 10 casualties per 100 rounds fired. Proximity-fused missions were producing 50 to 70 casualties per 100 rounds. The mathematics of attrition warfare shifted fundamentally. American artillery commanders began developing new tactical procedures specifically for proximity fuse employment. The concept of time on target, where multiple batteries fired so their shells arrived simultaneously, became even more devastating when combined with VT fuses. A standard time on target mission might involve 4 to 6 batteries, 24 to 36 guns, firing in coordination. When executed with proximity fuses, this created a steel cloud above the target area lasting several seconds. The psychological effect on survivors approached terror. German soldiers described the sensation of being caught under a storm of metal, with no escape possible, no action that could improve survival odds. Some units experienced what modern terminology would classify as combat stress reactions. Men refused orders to advance into areas where proximity-focused fire had been observed. The Third Army's drive to relieve Bastogne demonstrated proximity fuses employed at operational scale. General George Patton's artillery commander, Brigadier General Edward Williams, coordinated fire from 12 battalions totaling 144 howitzers. Between December 22nd and 29th, Patton's artillery fired approximately 50,000 proximity-focused rounds, according to Third Army ammunition expenditure reports. The effect on German defensive positions was catastrophic. The 5th Panzer Army, attempting to contain Patton's advance, lost cohesion as supporting infantry units suffered crushing casualties. Panzer formations found themselves increasingly isolated, unable to establish stable defensive lines because they lacked the infantry necessary to hold ground. By December 26th, when Patton's spearheads reached Bastogne, German forces in the southern shoulder of the Bulge were conducting fighting withdrawals rather than organized defense. The Battle of Elsenborn Ridge provides perhaps the clearest demonstration of proximity fuses at maximum effectiveness. This was the northern shoulder of the German offensive, where the 2nd and 99th Infantry Divisions held critical terrain against the 6th SS Panzer Army. The SS units included the 1st SS Panzer Division Leibstandarte Adolf Hitler, elite formations with years of combat experience. The American artillery supporting Elsenborn Ridge included elements of the 37th, 96th, 372nd, 955th, and several other field artillery battalions, a massive concentration of firepower defending a relatively narrow frontage. Between December 17th and 19th, these artillery units fired approximately 160,000 rounds. Historical analysis suggests roughly 40,000 of these were proximity-focused. The casualty exchange ratios were stunning. German forces attacking Elsenborn Ridge suffered estimated casualties exceeding 5,000 killed and wounded over 3 days. American defensive casualties totaled approximately 800. The artillery accounted for the majority of German losses. Survivors from SS units reported that entire companies disappeared in single artillery barrages. The Germans attempted tactical adjustments. Units began moving only at night, hoping darkness would provide concealment. But proximity fuses didn't require visual observation. American forward observers called coordinates based on sound detection, movement reports from outposts, and map analysis. The shells found their targets regardless of lighting conditions. Some German commanders tried dispersing their formations more widely, maintaining intervals of 50 to 100 meters between individual soldiers. This reduced casualties per impact, but also reduced unit cohesion and command effectiveness. A dispersed formation moved more slowly, communicated less effectively, and couldn't mass combat power when contact occurred. Others attempted using overhead cover. Troops sheltered in buildings, under bridges, in culverts, anywhere that offered protection from above. But this made units static, predictable, and vulnerable to direct assault by American infantry. Combined arms doctrine requires mobility. German forces that went to ground to avoid artillery became targets for infantry and armor. The most desperate measure involved attempting to capture intact proximity-focused shells for technical analysis. German intelligence officers issued standing orders that any recovered American artillery round with unusual characteristics should be immediately reported and secured for transport to rear area technical evaluation teams. The hope was that German scientists could reverse engineer the fuse design and develop countermeasures or produce German equivalents. Several intact fuses were indeed recovered. German technical evaluation teams, working at facilities near Berlin and in Austria, examined the devices with growing dismay. The miniaturization techniques were beyond German industrial capacity at that stage of the war. The vacuum tubes were smaller than anything German radio manufacturers had produced. The power supply system, the shock-activated battery, was elegantly simple but required precision manufacturing that German factories, operating under constant bombing pressure, couldn't replicate. More fundamentally, Germany lacked the raw materials. The proximity fuses required high-quality electronic components, specialized alloys, and manufacturing precision that demanded stable factory environments with reliable electricity and skilled labor forces. By late 1944, German industry was struggling to maintain production of conventional weapons. Developing an entirely new category of electronic fuses was impossible given resource constraints. German countermeasure research focused on jamming. If the proximity fuse used radio signals, perhaps those signals could be disrupted. Engineers developed several radio frequency jamming concepts, portable transmitters that might trigger premature detonations or prevent fuses from functioning. Testing showed some theoretical promise, but practical deployment was impossible. The equipment was too heavy for infantry to carry, required too much power, and didn't work reliably under field conditions. By early January 1945, German military intelligence had compiled comprehensive reports on American proximity fuse capabilities. These reports made clear that no effective countermeasure existed. Field units received updated tactical guidance, emphasizing the importance of overhead cover, night movement, and maximum dispersion. But these were desperate measures that acknowledged the fundamental problem without solving it. The human cost, as always in war, defies simple calculation. The proximity fuse killed efficiently. German soldiers died by the hundreds and thousands, killed by weapons that seemed to possess malevolent intelligence. Young men, many of them teenagers conscripted in the war's final stages, experienced death delivered from above, by invisible radar systems they couldn't understand or counter. American artillerymen firing the rounds rarely saw the effects directly. They stood beside their howitzers, loading and firing on coordinates provided by forward observers miles away. The rounds screamed into the sky and disappeared. Confirmation came through radio reports. Target destroyed. Enemy casualties estimated at 100 plus. Fire missions successful. The killing was abstract, numerical, reduced to logistics entries and ammunition expenditure reports. Yet moral responsibility exists regardless of distance. The proximity fuse was designed explicitly to maximize human casualties. Its entire purpose was to place steel fragments precisely where they would kill the maximum number of people. Engineers who developed the fuse, factory workers who assembled the components, artillery crews who fired the rounds, all participated in a system optimized for efficient killing. The ethical calculation of warfare is never simple. German forces in the Ardennes were executing Hitler's final offensive gamble, attempting to split Allied armies and recapture Antwerp. Their success would have prolonged the war, delayed the liberation of concentration camps, caused additional civilian suffering. Every day the war continued meant thousands more deaths in Nazi camps, more cities destroyed, more families torn apart. Proximity fuses shortened the Battle of the Bulge. They made German offensive operations prohibitively expensive in casualties. They forced German commanders to abandon attacks that might otherwise have achieved breakthrough. By making American artillery dramatically more lethal, they arguably saved American lives while taking German ones. The moral mathematics are uncomfortable but unavoidable. American casualties at the Battle of the Bulge totaled approximately 75,000, including 19,000 killed. German casualties approached 100,000. The disparity reflected multiple factors including American artillery superiority, air support once weather cleared, and defensive advantages. But proximity fuses contributed significantly to the casualty exchange ratio. Consider the counterfactual. Without proximity fuses, would German attacks have penetrated farther? Would Bastogne have fallen? Would Patton's relief operation have required more time? Each of these scenarios implies higher American casualties and potentially different operational outcomes. The weapon's strategic value extended beyond simple kill counts to its effect on German operational planning and execution. The industrial achievement deserves recognition distinct from its military application. American factories in 1944 produced 40,000 proximity fuses daily. This required coordinating 87 different manufacturing companies, operating 110 factories. The supply chain involved specialized components from dozens of suppliers. Quality control maintained standards that ensured shells fired from howitzers in Belgian winter conditions would function reliably. The miniaturization techniques developed for proximity fuses became foundations for post-war electronics industries. The vacuum tubes, shock-resistant component mounting, automated testing procedures, and quality control methodologies all transferred to civilian applications. Dr. James Van Allen, who designed many of the miniaturized components, later applied similar techniques to satellite instrumentation, ultimately discovering Earth's radiation belts. The organizational methods pioneered in proximity fuse production influenced modern supply chain management. Coordinating hundreds of suppliers to produce components, meeting exact specifications on precise schedules, required logistics systems that didn't exist before the war. The techniques developed to manage proximity fuse production became templates for post-war industrial organization. But in December 1944, these future implications were invisible. Artillery batteries in the Ardennes focused on immediate tactical problems. German formations needed to be stopped. American defensive lines needed to hold. The proximity fuse was a tool that accomplished these objectives with devastating efficiency. The German military leadership understood the implications. Field Marshal Gerd von Rundstedt, commanding German forces in the West, later testified that proximity fuses were decisive in stopping the Ardennes offensive. He stated explicitly that German attacks failed primarily because of artillery that possessed unprecedented effectiveness. German tactical doctrine couldn't adapt quickly enough to counter the new weapon. General Hasso von Manteuffel, commanding the 5th Panzer Army during the Bulge, described proximity-fused artillery as creating panic among veteran troops. Soldiers who'd survived years on the Eastern Front, who'd endured Russian artillery barrages at Kursk and Stalingrad, found American proximity-fused fire qualitatively more terrifying. The inability to take effective cover, the sense that the shells could find you anywhere, broke morale in ways conventional artillery never achieved. Statistical analysis compiled by American artillery officers in early 1945 revealed the weapon's impact. The 200,000 proximity-fused shells fired during the Battle of the Bulge accounted for an estimated 15,000 to 20,000 German casualties. This represented roughly 20% of total German losses in the battle, achieved with approximately 10% of total American artillery ammunition expenditure. The effectiveness ratio, casualties per round fired, exceeded conventional ammunition by factors of 5 to 7, depending on target type and tactical situation. Against infantry in the open, proximity fuses were roughly 10 times more effective than contact-fused shells. Against armor formations with supporting infantry, the ratio was approximately 5 to 1. Even against dug-in defensive positions, proximity fuses showed 2 to 3 times greater effectiveness than conventional time-fused airbursts. These numbers translated directly into operational outcomes. German units that might have sustained attacks for hours or days under conventional artillery fire collapsed in minutes under proximity-fused bombardment. The weapon didn't just kill more efficiently, it destroyed unit cohesion faster, disrupted command structures more completely, and created psychological effects that persisted beyond the immediate engagement. The Battle of the Bulge ended January 25, 1945, with German forces in full retreat. The offensive had cost Germany approximately 100,000 casualties, including 25,000 killed. Material losses included approximately 600 tanks and assault guns, over 1,000 aircraft, and irreplaceable supplies of fuel and ammunition. The strategic gamble had failed catastrophically. American losses totaled 75,000, including 19,000 killed. These casualties were severe, representing one of the costliest American battles of the war. But the defensive success prevented German breakthrough, maintained Allied momentum toward Germany, and demonstrated that American forces could absorb surprise attacks and maintain operational effectiveness. Proximity fuses contributed significantly to this outcome. They multiplied American artillery effectiveness precisely when it was most needed. They enabled smaller American forces to hold against larger German formations. They turned defensive battles into artillery killing grounds that German commanders couldn't overcome despite tactical advantages in surprise and local numerical superiority. The weapons release for ground combat use, initially controversial and delayed by security concerns, proved strategically decisive. General Eisenhower's later assessment that German possession of proximity fuses might have made D-Day impossible or prohibitively costly underscores their importance. The technology represented a force multiplier that could shift campaign outcomes. The broader implications extended beyond the Ardennes. Proximity fuses remained in American artillery employment throughout the remainder of the European War and in the Pacific Theater. They became standard ammunition for situations requiring maximum anti-personnel effectiveness. Artillery doctrine incorporated proximity fuse tactics as fundamental procedures rather than special techniques. The psychological impact on German forces persisted through the war's final months. German soldiers learned to fear American artillery in ways that went beyond rational tactical calculation. The knowledge that shells could find you in any cover except reinforced overhead protection created constant stress. Units assigned to sectors facing American artillery experienced morale problems that affected combat effectiveness. From an engineering perspective, the proximity fuse represented the first autonomous weapons system. The shell made its own decision about when to detonate based on sensor input and pre-programmed parameters. This autonomy, crude by modern standards, established principles that would evolve into guided missiles, smart bombs, and eventually autonomous weapons systems deployed in 21st century conflicts. The ethical questions raised by autonomous weapons, questions about accountability and proportionality, and the delegation of life or death decisions to machines, all have roots in the proximity fuse. The 1940s engineers who designed radar-triggered detonators couldn't have anticipated modern debates about artificial intelligence in warfare, but they established the precedent that weapons could incorporate decision-making logic. The strategic assessment conducted by Allied Command in the months following the Bulge confirmed what battlefield commanders already understood. Proximity fuses had fundamentally altered the tactical balance in ground warfare. The weapon didn't just improve artillery effectiveness incrementally, it represented a qualitative shift in what artillery could accomplish. Traditional artillery doctrine divided between harassment fire, designed to disrupt enemy movement and suppress activity, and destructive fire, intended to actually destroy targets. Harassment required modest ammunition expenditure, but achieved limited results. Destructive fire consumed enormous ammunition quantities and required sustained bombardment to achieve effects. Proximity fuses created a third category: efficient, destructive fire that achieved high casualty rates with sustainable ammunition expenditure. This shift had profound implications for operational planning. Artillery units that previously needed hours of sustained fire to neutralize enemy formations could now achieve similar effects in minutes. The time compression meant faster operational tempo, more rapid exploitation of tactical opportunities, and reduced vulnerability windows for friendly forces advancing under artillery support. The logistical advantages were equally significant. American supply lines in early 1945 stretched from Atlantic ports through France and Belgium to front lines approaching the Rhine. Every artillery shell traveled this entire distance, consuming transportation capacity and requiring handling at multiple depot stages. Proximity fuses achieved greater effect per round, meaning the same transportation assets could support higher operational tempo. Ammunition expenditure statistics from January through March 1945 showed proximity-fused rounds, comprising approximately 15 to 20% of total American artillery fire in the European theater. This proportion was limited primarily by production capacity and distribution logistics rather than tactical preference. Artillery commanders requested proximity fuses for virtually every fire mission against personnel targets. The weapon's success generated immediate demand for expanded production. American factories increased output to 70,000 fuses daily by February 1945. This represented the limit of available manufacturing capacity given competing demands for other munitions. The supply never quite matched demand through the war's end, with artillery units rationing proximity-fused ammunition for high-priority targets. German technical intelligence efforts, while unable to develop effective countermeasures, did achieve detailed understanding of proximity fuse principles by February 1945. Reports circulated through German command describing the radio-based detection system, the optimal burst height, and the fragmentation patterns. This knowledge didn't provide solutions, but did allow more realistic tactical planning. German defensive doctrine in the war's final months emphasized fortified positions with overhead cover, night movement, and maximum use of urban terrain where buildings provided protection. These measures reduced proximity fuse effectiveness somewhat but couldn't eliminate it. American artillery simply adjusted tactics, using proximity fuses for area interdiction while employing direct fire and heavy-caliber weapons against fortified positions. The Pacific Theater saw proximity fuse employment beginning in 1944 for anti-aircraft use and expanding to ground support roles in early 1945. Japanese defensive tactics, emphasizing concealed positions and prepared fortifications, presented different challenges than German mobile warfare. But proximity fuses proved effective in suppressing Japanese positions and inflicting casualties on troops moving between defensive positions. The Battle of Okinawa, lasting from April through June 1945, demonstrated proximity fuses in the island warfare environment. American artillery fired approximately 2 million shells during the campaign, with approximately 400,000 being proximity-fused. The weapon proved particularly effective against Japanese counterattacks and infiltration attempts, situations where American forces needed immediate defensive fire. Japanese after-action reports, captured after the war, described American artillery as possessing supernatural accuracy and effectiveness. Japanese soldiers reported shells that seemed to seek out covered positions that detonated precisely where they would cause maximum casualties. The psychological effect paralleled German experiences in Europe, creating fear that degraded combat effectiveness beyond simple casualty counts. The atomic bombs that ended the Pacific War in August 1945 overshadowed virtually all other weapons development in historical memory. The Manhattan Project's success and its strategic implications dominated post-war analysis, but proximity fuses, while less dramatic than nuclear weapons, had arguably greater impact on actual combat operations during the war years. Consider the comparative statistics. The two atomic bombs killed approximately 130 to 220,000 people, primarily civilians, in Hiroshima and Nagasaki. Proximity-fused artillery and anti-aircraft fire killed an estimated 35 to 50,000 enemy combatants across all theaters while destroying hundreds of aircraft. The proximity fuse was used in actual combat for over 2 years, while atomic weapons were employed twice in the war's final week. This comparison isn't meant to equate or minimize either weapon's significance. Rather, it illustrates that revolutionary military technologies don't always announce themselves through dramatic singular events. Sometimes they work through accumulated incremental effects across thousands of engagements. Proximity fuses changed warfare one artillery barrage at a time. The post-war period saw rapid declassification of proximity fuse technology. By 1946, the basic principles were public knowledge. American manufacturers began exploring civilian applications of the miniaturization techniques and quality control procedures developed for military production. The electronics industry, which would drive much of late 20th century technological development, had roots in wartime proximity fuse manufacturing. The organizational legacy proved equally significant. The coordination required to produce proximity fuses, managing dozens of suppliers and hundreds of component specifications while maintaining security and quality standards, became a template for complex manufacturing projects. Post-war aerospace programs, particularly missile development and eventually space exploration, used organizational structures derived from wartime fuse production. Merle Tuve, who directed proximity fuse development at Johns Hopkins Applied Physics Laboratory, returned to academic research after the war. His laboratory continued defense-related research, but also pursued fundamental science. The institutional relationships between universities and military research establishments, relationships that would shape Cold War science policy, were forged in programs like proximity fuse development. Dr. James Van Allen applied miniaturization expertise to instrument packages for early satellites. His sensors, using vacuum tube technology derived from proximity fuse work, discovered the radiation belts surrounding Earth, now named for him. The scientific achievements of early space exploration depended directly on techniques developed to make artillery shells more lethal. The ethical complexities of this technology transfer deserve consideration. Scientists who designed weapon systems to kill efficiently contributed, often unintentionally, to post-war technological development that improved civilian life. The same miniaturization that made proximity fuses possible enabled transistor radios, early computers, and eventually the entire digital revolution. Progress and destruction intertwined in ways that resist simple moral categorization. Military applications of proximity fuse principles continued through the Cold War and beyond. Guided missiles incorporated radar proximity fuses to improve kill probability against aircraft. Artillery continued using proximity fuses for anti-personnel missions through Vietnam, subsequent conflicts, and into the 21st century. The basic concept, a sensor that detects target proximity and triggers detonation automatically, became fundamental to modern weapons design. Contemporary smart munitions represent logical extensions of proximity fuse principles. GPS-guided artillery shells, laser-guided bombs, and autonomous weapons systems all incorporate sensors that detect targets and make engagement decisions. The progression from 1940s radar fuses to 21st century artificial intelligence in weapons systems follows a clear technological lineage. The Battle of the Bulge marked proximity fuses' combat introduction in ground warfare, but the weapon's influence extended through 7 decades of subsequent conflict. Every precision-guided munition used in modern warfare descends conceptually from those first proximity-fused shells fired over the Ardennes in December 1944. The soldiers who died under proximity-fused fire, German conscripts and veterans who couldn't comprehend the weapon killing them, experienced warfare's transformation into its technological age. They were casualties not just of a specific battle, but of a fundamental shift in how wars would be fought. Their deaths demonstrated that industrial civilization could produce weapons of devastating effectiveness, that scientific innovation could provide decisive military advantage. The American artillery crews who fired those rounds participated in this transformation, often without fully understanding it. They followed orders, loaded shells, pulled lanyards. The technology they employed would shape warfare for generations, but in the moment they focused on immediate tactical objectives. Fire mission coordinates, ammunition status, survival through another day of winter combat. Captain Parker's battery, mentioned at this narrative's beginning, continued operations through the Bulge and into Germany. They fired thousands of rounds, conventional and proximity-fused, supporting American advances through the Rhineland and ultimately to the Elbe. Parker survived the war, returned to the United States, and rarely spoke about his combat experiences. The technological revolution he participated in remained largely invisible to him, reduced to memory of cold mornings and the mechanical routine of artillery operations. The German column he destroyed on December 23rd represented one small engagement among thousands during the Battle of the Bulge. The casualties, perhaps 300 men killed and wounded, were statistically insignificant compared to the 100,000 German losses across the entire offensive. But those 300 men experienced firsthand what proximity fuses meant for ground warfare. They were among the first to die from weapons that possessed a crude form of artificial intelligence that made autonomous decisions about when to detonate. That transition, from human-controlled to autonomous weapons, would accelerate through subsequent decades. Modern warfare employs systems that identify targets, calculate engagement solutions, and execute attacks with minimal human intervention. The ethical and legal frameworks governing such systems remain contested and evolving, but the precedent was established in 1944 when artillery shells began making their own decisions about when to explode. The German soldiers advancing across that Belgian farmland on December 23rd couldn't have known they were experiencing warfare's future. They understood only that something had changed, that the American artillery possessed capabilities beyond previous experience. The shells detonated in mid-air with devastating precision. Cover provided no protection. Movement offered no escape. Death came from above, delivered by weapons that seemed to see them, to hunt them, to find them wherever they hid. This was the revolution proximity fuses represented, not merely improved artillery, but weapons that incorporated sensing, decision-making, and autonomous action. The radar systems were primitive by modern standards, capable only of detecting distance to ground. But the principle was established. Weapons could be designed to sense their environment and respond appropriately without human intervention at the moment of engagement. The technological progression from 1940s proximity fuses to 21st century autonomous weapons systems followed logical steps. Better sensors enabled more sophisticated target discrimination. Faster processors allowed more complex decision algorithms. Improved power supplies extended operational ranges. Each generation of weapons incorporated more autonomy, more decision-making capability, more distance between human controllers and actual engagement. Contemporary debates about autonomous weapons, about appropriate human control over life and death decisions, about accountability when machines make targeting choices, all have roots in that December morning when Colonel Axelson ordered his gunners to fire proximity-fused shells without authorization. That decision, made in tactical desperation, inaugurated an era of increasingly autonomous warfare. The mathematical precision with which proximity fuses killed, the optimal 30-foot burst height calculated to maximize fragment coverage, the radar systems that measured distance and triggered detonation, represented warfare's transformation into an engineering problem with optimized solutions. Human life became a variable in equations calculating lethal radius and fragment density. This cold calculus exists in tension with the human reality of warfare. Each German casualty from proximity-fused artillery was an individual with history, family, hopes, fears. The efficient mathematics that killed them doesn't diminish their humanity or the tragedy of their deaths. Technology makes killing more efficient but doesn't make it less tragic. The proximity fuse story ultimately forces confrontation with uncomfortable truths about technological civilization and warfare. Industrial democracies could produce weapons of devastating effectiveness. Scientific innovation could multiply military power. The same research institutions and manufacturing capabilities that created consumer prosperity could be redirected toward efficient killing. Progress in civilian technology enabled progress in military capability. These connections between civil and military technology, between scientific advancement and weapons development, between industrial capacity and military power, shaped 20th century history. The proximity fuse represented one moment in this larger pattern, but a significant moment that illustrated fundamental relationships between technological innovation and military effectiveness. From Captain Parker's battery engaging German armor on December 23rd, through the systematic deployment of 200,000 proximity-fused shells across the Ardennes, to the technological legacy extending into the 21st century, the proximity fuse story reveals how warfare transforms. Not through dramatic singular innovations, but through accumulated advantages that compound over time. The German Panzer columns that German commanders expected would split Allied armies and recapture Antwerp instead met artillery that possessed unprecedented effectiveness. The tactical calculations that suggested German armor could overcome American defensive lines proved incorrect because those calculations didn't account for weapons that would fundamentally change artillery's lethality. In the frozen forests and fields of the Ardennes, the age of technological warfare accelerated. The mathematics of death were rewritten by miniature radar sets in artillery shells, by vacuum tubes no larger than a fingertip, by engineers who designed weapons to kill with optimal efficiency. The German soldiers who died beneath proximity-fused airbursts were casualties of this technological revolution, participants in warfare's transformation, whether they understood it or not. Their experience, the terror of facing weapons that seemed intelligent, that found targets in any cover, that delivered death from above with mathematical precision, foreshadowed modern warfare. Every contemporary soldier facing precision-guided munitions, every civilian endangered by autonomous weapons systems, every person threatened by warfare's increasing technological sophistication walks paths first traced by those German soldiers in December 1944. The revolution begun when proximity-fused shells first detonated above German formations continues on modern battlefields, where autonomous weapons systems, guided missiles, and precision munitions dominate warfare. The technology has advanced beyond recognition, but the principle remains constant. Weapons increasingly make their own decisions about when and how to engage targets. Human control becomes more abstract, more removed from actual combat. Whether this progression represents progress depends on perspective and values. Proximity fuses shortened the Battle of the Bulge, saved American lives, hastened Nazi Germany's defeat. They also killed thousands of German soldiers efficiently, inaugurated autonomous weapons systems, and established precedents for removing humans from targeting decisions. Both consequences flow from the same technology. The proximity fuse achieved what its designers intended. It multiplied artillery effectiveness, provided decisive tactical advantages, contributed to Allied victory. It also transformed warfare, established dangerous precedents, and created ethical dilemmas that persist decades later. Technology rarely arrives without complications, without unintended consequences, without moral ambiguity. In the end, the proximity fuse story is ultimately about transformation and its costs. Tactical transformation that made American artillery devastatingly effective. Technological transformation that led from vacuum tube radar to artificial intelligence. Human transformation, as soldiers learned to fear weapons that seemed to possess intention and intelligence. Each transformation carried consequences beyond immediate battlefield effectiveness. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.